Good morning. Welcome to this fifth lecture of the course Compressible Flow and Gas Dynamics. In the previous lecture, we have discussed about the remaining fundamental concepts of the thermodynamics which are relevant for this course, and then I have also introduced nothing but the uh, concept of aerodynamic forces which are acting on the body. Okay, and mainly we saw aerodynamic drag and aerodynamic lift forces. After that, I gave you a brief idea about how to start uh, determining the governing equations for the flow problem. So if you see, in first case I had considered a finite sized control volume, and I told that if we use finite sized control volume, then we will be getting integral form of equations. Okay, if we use infinitesimally small control volume, then we will be getting differential form of equations. Okay, and in such scenario, if our length scales are so small that within the fluid domain we are having finite number of molecules, very less number of molecules, and where approximation of continuum cannot be considered, there we have to actually apply the equations for individual molecular motions. Okay, so and it was also discussed that that is something which is beyond the scope of this course. So here mainly in this particular course we will be referring either to the integral form of equations or to the differential form of equations. So some of the initial concepts we will deal with the integral form of the equations, and later on we will go to the differential form of equations. So that's why over here let's briefly talk about the governing equations, and whenever I will be describing the governing equations, I'll be dealing with finite sized control volume approach, and we will try to obtain the integral form of all the governing equations. Okay, so in terms of governing equations for fluid flow problems, we have uh, conservation of mass, okay, which is typically also known as continuity equation. Then we have another as momentum equation, and third one is energy equation. So these are the main fundamental governing equations. However, if we see in some situation that number of variables are actually not equivalent to the number of equations, then we take the help of some auxiliary equations. For example, if our working fluid is an ideal gas, then we consider an additional equation, ideal gas equation, etc. Okay, so now let's first talk about the conservation of mass equation. Okay, so to determine the conservation of mass, what we will do, we will consider over here a finite sized control volume. So say this is a control volume having volume v bar. Okay, and say this particular control volume is having surface area S. Now what I have done, I have considered a small element over the surface of this, and this element is having, say, surface area ds. Okay, and this element is so selected that it is having normal vector something like this, unit normal vector. Okay, so say let me use symbol n cap over here for unit normal vector. Okay, and obviously as this particular control volume is fixed in space, so if it is fixed in space, we will find that some of the velocities will enter through the boundary of this control volume and some of the velocities will go out. So fluid elements may enter from somewhere and may go out from other directions. Okay, so let's consider at this control surface, v vector is nothing but the velocity vector, and this is valid for this small control surface. Whenever we will be moving in other portions, then value of v vector may be different. Okay, now if you try to determine the amount of mass passing through this small control surface, then how much it will be? Amount of mass passing through ds. Tell me, how much will be the amount of mass which will pass through ds. So let's consider, because our volume is of finite sized, so inside this we can have variable density of the fluid. However, we have selected our element is so small that corresponding to this particular elemental portion, the density of the fluid is nothing but rho. So if rho is density of the fluid for this small element, then can you tell me how much will be the amount of mass passing through this ds? It will be rho times velocity vector times area. Okay, is this one clear? Velocity vector into area, that will form the volumetric flow rate, and if we have to determine the mass flow rate, okay, so I should also don't write over here say amount of mass, rather I should write rate of mass passing through this okay, so rate of mass passing through this ds. Okay, so we know that if this is the ds is the surface area and v vector is the velocity, then v vector dot ds vector, this will be nothing but, this will be the volumetric mass flow rate, and if we multiply this with density, then we will be actually getting the mass flow rate which is passing through this area. Okay, now remember what I am writing, I am writing over here in vector notation, so that's why I have used v vector dot ds vector. The reason is, what we have to do, this normal vector and velocity vectors are having certain angle. Okay, so always whenever we are estimating the volumetric flow rate or mass flow rate, we consider the component of the velocity which is parallel to the normal vector. Okay, so even further what you can do, you can write ds vector as n cap into magnitude, magnitude is ds. So if you do substitute, you will be finding rho v vector dot n cap into ds magnitude. Okay, now v vector dot n cap, what you will be getting, n cap is a unit vector and v vector is a velocity vector. So if you take the dot products of the two, you will be getting component of velocity vector along the normal direction. Okay, so this whole I can write as nothing but vn. So you can also, in simplified form, you can also write it as rho vn into ds. Okay, so you should be very clear where to put dot, where not to put dot. Okay, because dot carries some physical meaning. This is not just random thing that place it anywhere. Okay, so for example, when I am writing rho vns dns, so ds over here is a scalar, then vn is becoming component in x direction. Okay, so that's why whenever I am not putting any dot over here, where here I am considering the product of two vectors, then I have to consider the dot. Okay, okay, up to this it is clear. Now this is a small element we have talked about. If we have to determine the rate of mass flow through entire control surface S, then how we can determine rate of mass flow through S, control surface S? Tell me how we can determine it. So this is a small elemental surface. If we have to consider for the total surface, then we have to nothing but take the surface integral. Okay, so to depict the surface integral, I will use two integration symbols, and then I will write over here rho v vector dot ds vector. Okay, another interesting point is, whenever we are considering this closed volume, we are considering control volume, we are considering this as a completely closed from all the directions. Okay, so if we are considering it as a closed entity, so I can put over here nothing but a closed surface integral. Okay, so this is the reason I am putting over here a circle which is referring to nothing but the closed surface integral, entire surface integral. Even in reality, please note this point, in reality what will be happening, there will be some inlet port, some outlet port, something. So what I am doing, I am not considering any solid boundaries over here. So over here what we are considering, that anything is there, everywhere we have nothing but fluid, and we have created a hypothetical surface. So this is nothing but a hypothetical closed surface through which fluid is actually entering and leaving. Okay, so this should be clear that this is a hypothetical closed boundary of finite sized. So that is the reason I am writing over here this as a closed integral. Is this point clear? Now another interesting fact is there. If you see, this normal vector is pointing in outward direction, and this velocity vector direction also I have taken in outward direction. So it means we are considering a situation where actually mass is net mass flow is going out of the system. Okay, so in some portion of this one there may be inflow, there may be outflow, but what we have done over here, this v vector we have actually pointed in outward direction. So net mass flow rate we are considering in outside. So if we are considering net mass flow in outside, then we can also write rate of mass flow with some negative quantity. Is this point clear? Are you able to physically relate it? So there can be two things. Either you keep this positive, when you will be taking the rate of change of mass of this, there you put negative sign, or you do one thing, here you put negative sign, and in rate of change of mass you just keep it a positive quantity. Okay. But physical meaning is very clear, that what is happening over here, physically what is happening. Okay, so physically what is happening, that mass is actually going out of the system, that's why we are putting a negative sign over here. Okay, now so this is the total rate at which mass is going out of the control volume. Now this particular finite sized control volume will be having some volume also. So inside that volume also we will be having certain mass, and depending upon the rate, mass of this control volume will either decrease or increase with time. If total rate is outside, then it will decrease with time. If total rate is inside, then it will increase with time. So there will be a change in mass of the control volume with time. So let's consider in the center of this one, or say at any point, I have considered another small sized volume dV bar, and I have considered this such that this volume dV bar is having density rho. Okay, so mass of this element will be rho into dV bar. If we have to determine the mass of entire control volume, mass of fluid inside the entire control volume, then I can write volume integral. So volume integral over the closed entity dV bar. Okay, now this is the mass. However, we are having mass rate associated. So it means if there is no mass flow across the boundary of this particular control volume, then this will remain fixed. But as there will be mass inflow and outflow across the boundary of the control volume, so this particular mass will change with time. Okay, so rate of change of mass, rate of change of mass of control volume will be equal to del by del t, and then we will consider volume integral of rho into dV bar. Okay, is this point clear? Now the rate at which net mass is going out of the system, that must be equal to, out of the control volume, that must be equal to the rate at which mass of the control volume is actually changing. So I can equate, say if this is 1, this is 2, I can equate both of these quantities. If I equate these quantities, I will get del by del t rho dV bar equal to minus of surface integral rho v vector dot ds vector. Okay, and what I can do, once again one more approximation I can take it over here, because my control volume size is fixed and it is fixed in the space. So I can, this limit of integration is not changing, so that's why I can actually take this time inside. Okay, so del by del t of rho dV bar, and let's consider this to the other side, plus surface integral rho v vector dot ds vector equal to 0. So this is the important equation. This is nothing but the integral form of continuity equation. And the beauty of this equation is that this is applicable for both incompressible and compressible flow situation. Okay. Another interesting fact is that whenever we will be talking about the momentum equation, there we will be finding that there are certain terms in the equation which are actually due to the viscosity of the fluid. So if we omit these terms, then our equation will be valid only for the inviscid flow situation. But in our momentum equation, any such issue does not come, and this equation is actually valid for both inviscid and viscous fluids. However, if we further simplify it and try to take out some of the terms, then this may become specialized for certain flow situations. Okay. So, but over here I have referred to the very generic portion of this equation. Now let's talk about the next equation, that is nothing but our momentum equation. Okay. So momentum equation is nothing but the consequence of the Newton's second law of motion, according to which we are having rate of change of momentum is equal to the, what is Newton's second law of motion? Force equal to mass into acceleration, or in more generic sense it says that rate of change of momentum is equal to force. So it means d by dt of m into v, velocity, okay, is equal to force. Now we consider that, say for a given fluid entity, mass of the fluid entity will be fixed. So then we write m into dv by dt equal to, so let me write it in vector notation only, this is force vector. So then then this m dv vector by dt becomes nothing but the acceleration vector equal to f vector. So this is the Newton's fundamental definition of Newton's second law of motion. Whenever we will be applying this particular law on our fluid element, okay, then what will be happening? We have to determine this acceleration for the mass of the fluid element, and we have to determine this force. Okay. So let's first talk about what are the forces which can act on a fluid element. So fundamentally we have two types of forces, body forces and surface forces. Fine. So body force over here for this particular fluid element will be due to the acceleration due to gravity. Okay. Or if our fluid element is in some another external flow field, so any force which is acting due to the mass of the fluid element whenever it is placed in an external field, okay, external fields such as electric field, magnetic field, gravitational field, then actually it experiences the body forces. Okay. So say over here small f, so this is little bit bold in vector notation, let me put vector over this only. So f vector is say our external force per unit mass, external force vector on per unit mass basis. Is this one clear? Now when we will be talking about the surface forces majorly will be in the form of pressure and shear force. Now shear stress, basically I should not say shear, I should write more generic term as the viscous force, because viscosity also causes normal stresses as well. Okay. So I will be having pressure as well as the viscous forces. Okay, so for the time being, as I explained you in the previous lectures, that particularly majority of the components in this course we will be dealing as reversible adiabatic. If we are considering the reversibility, then we have to remove all the irreversible effects. Okay, so viscosity is nothing but the consequence of friction, which is the major cause of irreversibility. So for the time being, we will actually not consider this viscous force. Okay, so viscous force we will not consider for our formulation. So majorly we will be considering nothing but the pressure forces over here. Okay, is this point clear? Now let's talk about the same fluid element. So the same fluid element which I have explained you earlier, that is its small elemental volume is having mass rho into dv bar, and this mass is when placed in external force field which is having force vector per unit mass as F vector. So it will experience the force uh, with multiplication of F vector. This will be the body force on dv bar. Okay. However, what will be the body force on total fluid element? Complete fluid inside control volume. What will be the body force on this? Volume integral of rho F vector dv bar. So please make difference between bar and vector. Okay. Is this point clear? Now let's talk about the pressure force. Let's consider that this is my ds, this is the normal vector. Now pressure will be acting something like this, compressive force. Okay, so I will be having on this small element ds, pressure force will be P into n cap ds, and pressure force on complete surface S will be surface integral. Once again, remember one thing, pressure and normal are having the opposite direction, so we have to put over here the negative sign. Okay, so this will be minus of P in ds vector. Is this point clear? So this is the total pressure force which is actually acting. Now viscous force we will not consider over here. So it means we have accounted for all the forces. Okay, so my equation is rate of change of momentum means m into dv vector by dt equal to f. So we have determined the f, which is volume integral of rho f vector dv bar minus surface integral of p into ds vector. Okay, so this is the net force. Now yes, uh, you have not attended the previous lecture. So I told that majority of the time in the compressible flow situations we will be dealing with the reversible flow situations. Okay, and for majority of the instances even reversible adiabatic situations. Okay, so basically what happens when we have the high speed flows over the objects, so we find that there will be a very thin boundary layer formation, and within the boundary layer zone only we will be having the viscous effects dominant, and in majority of the fluid portion away from the boundary layer we will be having inviscid flow kind of situation. Okay, so that is the reason that majority of the compressible flow situations can be accurately analyzed by just considering the reversible flow situations. Okay, so if you are not coming, then at least go through the recording. Okay. Okay, so now what we have to do? We have to find this m into dv vector by dt. So tell me, what are the momentums associated with this? First thing is, we have seen that rho v vector into ds amount is going out. Rho v vector dot ds vector. This much amount is going out. So whenever this much amount is going out, it is going with certain velocity. So it will also carry some momentum. So I will be having one more v vector over here. Okay. So what I can say that, I can say that momentum carried by outgoing fluid through control surface S. Okay, so here I will be having automatically surface integral. Mass which was going out was rho v vector dot ds vector, and then here I have to put one more velocity vector. Now do I put here dot sign outside bracket? What is this inside? This dot product has already become a, so scalar is getting multiplied, so I should not put now the dot sign. Okay, is this one clear? Now here when we have accounted this momentum change, this momentum is only which is going through the boundary of the control volume. However, there can be momentum change within the control volume. So just now we said that if say inflow and outflow rate of mass is not matching, then there will be either increase or decrease in mass of the control volume. So if mass of the control volume within its volume is changing with time, then its momentum will also change with time. Okay, and another situation can also be there. For example, if you have a pulsating flow situation, you have some nozzle as your control volume, and in that nozzle you are switching on and switching off the valves periodically. So what will happen? The inflow and outflow of the mass will vary with time. If that is varying with time, that will change the overall momentum within the control volume. Okay, so rate of change of momentum within the control volume, particularly for mass of the control volume with time, that now we need to determine. Okay, is this one clear? Within control volume, this will be equal to del by del t volumetric integral of rho, sorry, dv bar times v vector. Okay, because v vector is the say velocity vector associated. Fine. Now once again this del by del t I can take inside. So now left hand side of the equation have we quantified? So if you see left hand side of the equation also we have quantified. So if we take the sum of both these left hand side terms, which represents the change in momentum, so I will be finding volumetric integral of del by del t rho v vector dv bar, okay, plus surface integral of rho v vector dot ds vector v vector, that is equal to minus surface integral of, from the previous slide, p ds vector plus integral, volume integral of rho f vector dv bar. Okay, so this is my momentum equation. So majority of the time actually, if earlier you have done the derivation of the momentum equation in your earlier courses, you might have done it using the differential approach. In differential approach, there also there is a lot of physical explanation associated, but majority of the time we don't go in much deeper into the physical formulation. Whereas if you try to derive the momentum equation from the basically particularly from the principle of in the integral form, then you will be actually able to relate each and every step with the actual physical phenomena which is happening within the control. Okay. So this is our momentum equation. Now you see the final form of the momentum equation. In each and every term we have one vector term. So this entire term will give nothing but a vector. This will give a vector. So the reason is, in case of momentum, we will be having actually, we are making equal force and momentum. These are the vector quantities. So we will be having components in each and every direction. For example, when we consider the momentum equation, we say x momentum equation, y momentum equation, z momentum equation. So we are having the components in each and every direction. So that's why this entire equation is actually coming in nothing but the vector form. Okay. So because of this vector form, actually this will give you the three different components in x direction, y direction and z direction. So all the three momentum equations are coupled inside a single equation. Okay. Another important point of this equation is that because it is in the vector notation, okay, so this makes it generic equation for all coordinate systems. How? Can you tell me? If you take the Cartesian coordinate system, then you will be writing this v vector in such a way you are having the components of velocity along x, y and z direction. If you take cylindrical coordinate system, then you will be considering the components of the velocity, particularly this v vector, in such a way that it is considering the components along r, theta and z direction. If you consider in spherical coordinate system, then components of velocity vectors are to be written along r, theta and phi. So this is the most generic form of the equation because it is in the vector notation and it is applicable for all the coordinate systems. The only change will be happening whenever you are considering the velocity vector, that particular velocity vector you have to actually consider for that particular coordinate system which you are considering. Okay. So this is the equation which will be applicable for majority of the compressible flow situations. However, if you have to make it generic, more generic, then one more force should be considered, which is due to normal and shear viscous stresses. Okay, because of these stresses, whatever the force we will be getting, that is F viscous. However, in this particular course, mainly we will be actually omitting this part, and whenever needed, then specifically we will be choosing for some special situations. Is this point clear? So this is the more generic form of the equation, and whenever we neglect this, then many times we call this equation as nothing but the Euler's equation. Okay, if we neglect viscosity, if we neglect the viscous forces, then it is called as Euler equation. If you consider the viscous forces, then actually it becomes more general form, Cauchy form of momentum equation. And when you even substitute the viscous forces for a Newtonian fluid, okay, the approximation of constant viscosity, then we call the equation as nothing but the Navier-Stokes equation. Is this point clear? Okay. So now, whenever we deal with the incompressible flow situation, then particularly when energy transfer is not involved in our physical situation, then momentum and continuity equations are sufficient enough. However, for compressible flow situations, as we saw in our very first lecture, that changes in density of the fluid element with change in pressure does not keep other thermodynamic properties of the fluids fixed. So other thermodynamic properties of the fluid also varies. It means energy content of the fluid also changes. So these two equations will not be sufficient enough, and we have to also consider the energy equation also. Okay, so even if you say in your physical situation there is no heat transfer involved, then also if you are solving a compressible flow situation, you have to consider the energy equation, because there is change of energy when compressibility of the fluid is actually coming into picture. Okay, is this point clear? Okay, so let's now talk about the energy equation. Tell me, what are the components of energy equation? We consider that in case of energy equation, we consider that net rate of heat transfer, if say work is done on the fluid, then I will consider plus net rate of work transfer is equal to change in total energy of the system. So, or in very generic sense, say I consider some symbol B1 as total heat transfer rate. Okay, B2 as work transfer rate, then I will be having B3 as energy change rate. Okay, is this point clear? Because of the heat and work transfer across the control surface, we will be finding that there will be change in energy content of the system with the time. So rate of change of energy with time I am referring to as nothing but the B3. Okay, now let's first talk about the heat transfer effect. Let me once again emphasize, whenever we will be considering now the heat transfer effect, we have to consider the heat transfer that is possible in a reversible way. Okay, so if you see among the different modes of heat transfer, we have conduction, convection and radiation. So conduction and convection will always be requiring some temperature gradient for the heat transfer to take place. Okay, so in this situation what will be happening, whenever we are assuming the reversible flow situation, okay, so then heat transfer through finite temperature difference is another major cause of irreversibility. So we will not be considering the temperature difference between the fluid layers. So it means we are not considering over here the conduction and other diffusive effects for the transfer of the heat. Okay, so first thing is conduction and other diffusive effects are negligible. Is this one clear? So now it means that we will be having the transfer of the heat, say, because of the radiative effect. So whenever we are considering that, majority of the time we will be dealing with the volumetric with the gaseous fluids. Okay, so whatever the heat is coming to the fluid medium because of the radiations, that will be nothing but accounted in the form of volumetric heating of the fluid. Is this one clear? What I am saying? Say you, this is the room. In this room you have what? Air. If radiations are coming to this room, so we are saying that this radiation will heat the air molecules at each and every portion of the room. So it means it is heating the medium in the form of volumetric heating. Is this point clear? So now let's consider Q dot is the rate of heat addition per unit mass. Okay, if Q dot is rate of heat addition per unit mass. So for a small elemental volume, we will be having mass as rho into dV bar. So rho into dV bar and Q dot will become the net rate of heat addition for this one. Okay, so this is the net rate of heat addition. Now the net rate of heat addition for entire control volume is how much it will be? So volume integral of rho Q dot, sorry, I made a mistake. This should be dV bar, not vector. So this is the total rate of at which heat is actually added to the control volume. So I must equate this to equal to B1 because the conduction and other diffusive effects over here are actually negligible. Is this one clear? Now we will be talking about second as the work transfer. So whenever we will be considering the work, once again viscous forces we are neglecting. So any work which is rate of viscous work transfer we are actually neglecting over here. Okay, so first we will be having work interaction because of the pressure. So because of the pressure, work interaction will be how much? What is the pressure force? Integral P into ds vector. Okay, so how much will be the force? So if you see, to understand this, because of a force, so this is nothing but a P into ds bar is a force vector. Okay, what is this? This is a force vector. Is this one clear how it is a force vector? Pressure when multiplied with area becomes, so I am multiplying pressure with the force vector over here. Area vector over here. So when pressure is multiplied with area vector, it becomes nothing but a force vector. So this is a force vector over here. Okay. Now consider a simple situation. Say I have some object. This is subjected to some force vector F vector, and say in some time delta t it changes through some distance dr vector. Okay, and say if I consider any point away from this as origin, where this is r1 as the position vector of the object, and after some time object will be over here, this is r2 as the another position vector. Okay, so now if you have to determine the work associated with this rate of work, rate at which work is done on this object by this force, that will become F times dr by dt. Okay, so it means it will become dr by dt will nothing but be velocity. Okay, this will be the velocity of the object. So if it is moving in this time dt, then I will be finding this is becoming F vector dot v vector. Is this one clear? So it means if you are having a force vector, if you multiply that force vector with velocity vector, then you will be finding nothing but the rate of work transfer. Okay, so here pressure is also nothing but a, what is this pressure into ds bar? This is nothing but a force vector. Okay, so rate of work transfer due to pressure force is how much? Minus surface integral of p ds vector dot v vector. Okay, similarly rate of work transfer due to body force, due to body forces, this will be equal to, what is the magnitude of body forces, volumetric integral rho f vector dv bar. Okay, this whole we have to take dot product with the, is this one clear? So the sum of both these two quantities will form nothing but my, because we only have considered in our momentum equation the pressure force and the body force. So sum of these two quantities is becoming nothing but my B2 term. Okay, this is the rate of work done on the fluid element. Okay, now we have another thing, that is actually right hand side of the equation, and right hand side of the equation we have actually, we have to determine change in energy content. Okay, so change in energy content, you can see uh, some mass is going out, so this will carry some energy also. So what is the rate at which mass is going out? S rho v vector dot ds vector. So this is the mass which is going out. Okay, now this mass, we know that thermodynamically any mass which is going out, that carries some energy, and that carries energy in the form of two forms. One is due to its physical state, and another is due to its thermodynamic state. So due to the physical state, energy carried by it will be kinetic energy and potential energy. Okay, so let's consider that change of elevation is not much significant over here, so potential energy is almost negligible. Okay, so we'll be having some kinetic energy change. We are saying that this fluid is having v vector as the velocity. Okay, so we will be having kinetic energy per unit mass as v square by 2, which is coming because of its physical state, plus we will be having some energy which is coming because of its thermodynamic state, and because of the thermodynamic state, which is the energy which is carried by the fluid, that is called as internal energy. Okay, so U, this is the specific internal energy. So energy change associated with fluid passing through control surface, that is nothing but equal to surface integral of rho v vector dot ds vector times u plus v square by 2. Is this one clear? Now another thing can be changes in energy within the control mass of the control volume with time. Okay, so rate of change of energy within control volume with time, that will be equal to del y del t of volume integral rho dv bar is the mass, and energy associated with this will be u plus v square by 2. Okay, so sum of these two quantities is forming nothing but my B3. So if we do so, I will get my energy equation finally in the form, once again del by del t I am taking inside. Okay, so volume integral del by del t of rho times u plus v square by 2 into dv bar plus surface integral of rho v vector dot times, so this is the right hand side B3 term. This must be equal to heat transfer. Heat we have considered in the form of volumetric heating rho q dot dv bar, okay, plus work done by the body forces on the fluid element, that is body force, once again a volumetric integral, okay, rho f vector dot v vector dv bar minus work done because of the pressure forces, that is surface integral of p ds vector dot v vector. Okay. So this is nothing but the energy equation. Now remember, now you observe one thing, any vector term is actually becoming scalar over here. Okay. So if you see, energy is nothing but a scalar quantity. So that's why each and every term of this equation is becoming a scalar quantity. Okay. Now one important point, this equation does not consider viscous work. It does not consider heat transfer due to conduction and other diffusive effects. Okay. And third is, if you consider a control volume where you rotate a shaft, we do consider in our thermodynamics. Okay. So if shaft is rotating and it is connected to some impeller, it will do some work on the fluid element. So over here we have also not considered that particular shaft work also. Okay. So W dot shaft is also not considered over here. So in case shaft work is given, we have to explicitly add it over here as the W dot shaft. Is this one clear? So is this energy equation derivation clear to you? Okay. Now, when we study the compressible flow situation, then obviously, as I told you earlier also, along with the mass and momentum equation for a flow situation, we have to parallelly solve the energy equation. Okay. Whenever we will be parallelly solving the energy equation, we will be finding the deficiency of equations. So you will find that your number of variables will become more than the number of equations. In that scenario, we also have to take some auxiliary relations which gives the relationship between different properties. Okay. So one such equation, which is majority of the times we will be using over here, because in compressible flow analysis we will be considering that our gas is nothing but a calorically perfect gas. So for a calorically perfect gas, I can write one relation as P equal to rho RT. We have derived earlier. So this is one important relation we will be using. And another, we know that internal energy for a general system or for a simple compressible substance is function of temperature and specific volume. However, for an ideal gas, it is nothing but a sole function of temperature. So this is also another important relation which we will use. And even when we will use this for a calorically perfect gas, then I can even write du equal to Cv times Tt. Okay. So say these I can consider as the additional equations which are coming because of the nature of the fluid which we are considering in our flow situation. And basic idea of these equations is to help us in maintaining the number between the equations and variables. Okay. Is this point clear? So these are the actually fundamental governing equations for compressible flow situations. Now what we will do, initial some of the lectures we will try to see the applications of these equations for different compressible flow situations. Okay, and then in the later stages of the course we will also derive the differential form of the equations, and then we will use these also for certain other flow situations. Okay, so now I will stop at this point, and if you have any questions that you may